Welcome to today's webinar, The Lifecycle of an AWS IoT Thing from Manufacture to Retirement. Our presenter today is Ian Massingham. Ian has been working with the cloud computing technologies since 2008. In his role, he works to increase the awareness of the AWS Cloud services and works with customers of all sizes, from startups to large enterprises. It helps them benefit from the adoption of AWS. He has a special interest in the development of connected device and the IoT applications, and in architecture patterns for the development of large-scale gaming platforms in the cloud. Today with us, we have the live Q&A moderators, which is Ryan Burke and Ben Moore. They'll be answering your questions throughout our presentation today. So with that, let's move over to Ian's presentation.
And welcome to this AWS webinar. My name's Ian Massingham. I'm a technology evangelist with Amazon Web Services located in Europe, and I'm going to be hosting this session today. At the end of the presentation, we're going to be joined by some other members of the AWS team who are going to be helping with Q&A during this session. So if you do have questions, please submit those using the webinar interface, and we will get to those at the end of the session. You can find me on Twitter, by the way, if you're interested in keeping up with the life of an AWS evangelist over here in Europe. Now, the topic for today's session is the life of an AWS IoT thing, and we're going to cover several different subtopics here to illustrate to you how you go about managing the life cycle of the devices that you need in order to build connected device applications. Before we do that, we will be taking a look at things like device prototyping, handling cryptographic keys and certificates, approaches for registering devices and attaching policies, working with the IoT Thing Registry, and then of course communicating with things and storing and retrieving device state using the AWS IoT Device Shadow. Before we do that, just a very quick introduction to AWS IoT. So what is AWS IoT? Well, AWS of course is a collection of web services that developers can use to build, deploy and operate scalable, secure and sophisticated applications. These applications can fit into a wide variety of different use cases, from websites and web apps through to analytics and machine learning, as well as traditional enterprise applications of course today. As far as IoT applications are concerned, what we've seen for quite a while actually is customers are using the AWS Cloud to build these kind of applications, and they're using the web services components that AWS provides in order to simplify that process and make it easier for them to develop, deploy and operate and scale these large-scale connected device applications. And we've got customers using AWS like Tile, and they have a Bluetooth low energy tracker which you can connect to your car keys or put in your luggage, and it will help you, enable you to locate those little tracker devices worldwide using a network of mobile apps. Sonos, another AWS customer, and Philips Healthcare, of course, who connect medical imaging devices to the cloud, taking advantage of the secure and compliant platform that AWS provides in order to deliver a new customer and patient experience for the people that are using and benefiting from things like connected X-ray devices, connected CAT scanners, connected MRI machines. So we have a wide range of usage of AWS for connected device applications today. And prior to the launch of AWS IoT, customers would build on these familiar hyperscale cloud services that we provide. So things like DynamoDB, it's a fast, predictably performant, non-relational data store. Amazon Kinesis, which is a mechanism for maintaining ordered streams of data in the cloud that you can then process and consume with a variety of different applications. These components were in use by customers that were building IoT applications before we launched AWS IoT. When we launched that service back in November 2015, so we're coming up to a year since the launch right now, we really wanted to focus on trying to simplify and accelerate the creation of IoT applications for developers, and that's really what AWS IoT does. And of course, during the course of this session, I'm going to describe to you a little bit more about how you can put the service to work for particular use cases that are prevalent in connected device applications. But what we're really trying to do here is create an environment where developers can securely connect devices to AWS at any scale to enable them to interact with applications and interact with other devices. There are a few different components to the service which we're going to cover in more detail through the session. A message broker, security components, a rules engine, device shadows, and a device registry. The whole thing comprises a managed platform that you can use for building and operating connected device applications, and it offers seamless integration with other AWS services. This is a very important component of the AWS IoT service. And once again, we're going to return to that later in the session and describe more about how that works. This is the architecture for the AWS IoT service. So out on the left-hand side, we have devices connected using the AWS IoT Device SDK. Then we have an authentication and authorization capability, which is delivered via a device gateway, which supports MQTT and WebSockets connections from your devices. That in turn is connected to a rules engine, and also using functionality that's present in the SDKs is used to deliver a set of features around device shadowing. Now, device shadows allow you to store and retrieve device state regardless of whether or not devices are powered on and connected, and you can asynchronously synchronize device state from the shadows to your connected devices. Again, we'll return to this in more detail later in the session, but it allows you to build applications that connect and read and write from shadows at any time using a web services API predictably. And that means that you can build applications where intermittent connectivity could be a challenge, or where you want to operate in a low power consumption environment where your devices are not persistently powered. So there's quite a lot of capability there in the device shadows, and as I said, we're going to return to that later in the session and discuss that in more detail. Then we have a device registry that allows you to store metadata about your device fleets, and we have an API, of course, for controlling everything, which is expressed via the AWS CLI tools, as well as expressed through a variety of different software SDKs or SDKs that you can use to manipulate the control plane of the AWS IoT service. So you can automate things like device registration and many other tasks that you might need to carry out in order to operate connected device applications at scale. After that quick intro to the architecture, let's move on and take a look at the device lifecycle. So the first thing is device prototyping. And in prototyping devices for AWS IoT, you're likely to be working with the AWS IoT Device SDKs. There are 5 of these today for physical devices, as well as 2 for mobile platforms. The physical device SDKs cover C and C++ for embedded operating systems, JavaScript, which is good for embedded Linux platforms, an Arduino library for the Arduino Yun. The Arduino Yun is a hybrid Linux Arduino device that features a Python SDK on the Linux platform, plus an Arduino Sketch SDK, an IDE on the Arduino half of the platform. So we have a specific library for that hardware platform. Then we have Python and Java SDKs, which are newer, and there's full details, including details of the launch of those 2 new SDKs available at the URL that you can see bottom right on this slide. And then we have mobile SDKs for iOS and Android, which can allow you to build the interface components for connected device applications on mobile platforms if that's something that your particular use case or your particular product demands. Now, there's a variety of different options for prototyping, of course. One of my personal favourites is prototyping with the Raspberry Pi. I would say that, of course, as a Brit, developed here in the UK and available globally. It's a low-cost ARM-based microcontroller board which runs Linux, a derivative of Linux called Raspbian, and has a variety of different electronics and sensor interface capabilities, which really pivot around this GPIO interface which is present on the board, which you can see here. Something called the Sense Hat, which I showed on the previous slide, which is a pre-integrated electronics package with an 8x8 matrix display and a variety of different environmental sensors. That's controlled using a Python module that you can see at the bottom of this slide via that URL. And then if you want to use the GPIO natively, there's a variety of digital and analog inputs there. You can use an embedded C library called Wiring Pi to do that. and that has associated with it a Python wrapper module that allows you to interface with the GPIO via a Python SDK as well. This is excellent for prototyping, and one of the reasons for that is you've got full-blown Linux running on the device, so you can use Git and GitHub for deployment of your connected device applications. You can compile components on the device, and you've got good logging and debugging capabilities available to you as well. So that's my own favorite prototyping platform. Now, of course, that's quite a heavy device in IoT terms, and AWS works with a wide variety of device manufacturers that make much more lightweight in terms of CPU and power requirement devices that you can use. And there's full details of these available on the IoT section of the AWS website, which we'll show you at the end of today's session. But essentially, these electronics manufacturers and distributors create prototyping platforms for AWS IoT and can help you move from a device prototype in the form of one of these IoT starter kits through to a product that you're going to manufacture in volume in order to launch a product or service based on AWS IoT. These are predominantly programmed using the Arduino IDE, but there are also other options. I encourage you to take a look at the IoT starter kits section of the AWS IoT website for more details on that. What you're building with your prototype is a thing that is capable of interfacing with the AWS IoT platform, which will be the primary point of interface for the back end for your application. And those interfaces really take two forms: pub/sub messaging via MQTT topics via the AWS IoT gateway, and then built on top of that actually state synchronization using the thing shadow. And this, if you maintain those interfaces that you've built using the same topics and using the same device state model in your thing shadow, it's very easy for you then to move from prototype to production. You don't have to change anything at the back end as you start to scale up your application and deploy more units of whatever your things are in order to fulfill the business model that you have in mind. So just bear that in mind, that if you keep those interfaces standard, it's very easy for you to change the hardware that you use on the device. For example, the AWS IoT button, which has been talked about on some previous webinars, you can build a prototype of that, a sort of reverse prototyping exercise using a Raspberry Pi or an Arduino, as long as you're generating the same types structure of JSON in the pub/sub messages that you're sending via the MQTT topics, and that your state representation model is of course the same as well. So you're going to accept the state synchronization and send and receive messages in the same format. It doesn't actually matter whether your hardware is a Raspberry Pi, an Arduino prototype, or a fully integrated manufactured product. The experience can be the same regardless of what the hardware type is. So just bear that in mind when you're thinking about prototyping. Okay, so we want to connect our devices, don't we? We're talking about connected device applications here after all. So how do we go about doing that? Well, we need device keys and certificates in order to authenticate and authorize communications from our devices to the AWS IoT service. And you remember from my architecture diagram that AWS IoT includes this security layer for authentication and authorization. And this is achieved using mutual TLS auth. Okay, now this is slightly different to the traditional unidirectional authentication that we're familiar with websites, for example, which you can see at the top here. So when establishing a connection to an SSL/TLS protected website, the website has a certificate, okay, which has been signed by a certificate authority. You're anonymous when you connect to it because it doesn't need to authenticate you. You need to authenticate it because you're going to be sending information to it. But in the vast majority of cases, it is not going to be sending information to you that requires authentication of your identity. There's a contrast here with IoT where we want to have mutual proof of identity. So in order to support that, we use cryptographic certificates at both ends of the connection. So the device itself needs an X509 certificate that's been signed by a certificate authority as well as a private key. And the gateway similarly needs an X509 certificate and a private key. And the certificates are exchanged by the two ends of the connection in order to provide cryptographic proof of identity and provide proof that both ends of connection hold the corresponding private key, of course, without sharing that private key, which obviously they need to retain control of. So this is how the mutual TLS authentication within AWS IoT works. It's actually very important for safety critical use cases, for regulated use cases, and you do not want to exchange information without proven identity. Making use of the mutual TLS-based, certificate-based authentication that's built into the AWS IoT service allows you to secure access to your devices and applications by applying policies, and we'll come to policies later, that are associated with specific certificates. Okay, so that's how we build the security and trust framework that protects data and provides proof of identity within applications of this type that you're going to build. So next thing we're going to do is move on to a quick demo where we'll take a look at using the AWS IoT console to create certificates and keys for connecting new devices. So I'm logged into the AWS console here in the Frankfurt region, which you can see in the top right just here. And I'm obviously going to be using the AWS IoT service here, which is indicated here by this blue icon. So I'm going to click into this. And here we are. I'm in the console now. This is the first run experience. I have no devices and no other resources that have been created in this region. So I'll see the first run experience here. If I already have resources here, I would see the regular console. If I hit get started, I can then create a thing. And I'm going to create a demo thing here. I could choose a thing type, which we'll come to later, if I wanted to do that. Hit create. And you can see there that I have successfully created my thing. If I click on this thing now, you'll see that the detail panel opens up in the right hand side of the console, which we can see over here. And if I go to connect a physical device to this thing, I'm then given the opportunity to work with one of the different SDKs. Console support is there for 3 of the available SDKs at this stage, but if I go for the embedded C option, you'll see that I'm asked to generate a certificate and a policy. And if I hit that generate a certificate and a policy button, you'll see that I then get a one-time opportunity to download my public key, my private key, and my certificate. Obviously those will end up getting saved in this case in my downloads folder on my Mac. So I've saved those, and then I can hit confirm and start connecting. And at this stage it automatically generates a C header file that's required in order to configure the AWS IoT SDK for embedded C. If I was to download and install that on my device, I would then just drop this header file into the source directory with the samples there, compile the sample, it would import the header file, and that would include details of the keys that I've just downloaded, also my account specific AWS IoT endpoint, the client ID and thing name that I specified when I built the logical representation of the device just there. The other thing that you do need to get is a root CA certificate, and there's details on how to download that in the SDK instructions, which you can find here. If you click this link, it'll take me off to GitHub, and the SDK instructions are there, including details of where to get hold of the root certificate, the default root certificate. Okay, so that's a very quick and very simple demo of creating device certificates and keys using the AWS IoT console. Of course, you can perform that same operation using the AWS CLI as well. And you can see an example here, AWS IoT create keys and certificate with hyphens, and then -- set as active also with hyphens. And that'll create you a public-private key pair and a certificate signed using the default CA, certificate authority. And for attaching a policy to a certificate, which you'll see a little bit later on, you need to make a note of that certificate ARN that you can see at the top there. That's the unique identifier for the certificate within your specific AWS account. So CLI is also an option. Obviously, you're more likely to use CLI or SDK-based certificate and key generation than you are the console when you get to scale. And talking of scale, we're going to move on now and take a look at getting keys and certificates onto your devices. And at the prototyping stage, this is very simple. You're going to copy or flash them together with the certificate authority cert onto your device. You're going to specify in your device side code, either one of our SDKs or your own native code, where your certificates, keys, and your certificate authority cert are located. And that's it. Very, very simple. Obviously, this gets a little bit more complex in volume manufacturing of devices. You're still going to be copying or flashing keys and certs, but the numbers of keys and certs could be quite high. You know, if you're manufacturing 10, 20, or 100,000 devices, then that's 10, 20 or 100,000 key and certificate pairs that you need, and that's quite a lot. So in this scenario, it's quite likely that you'll use SDKs or CLI to automate key and certificate creation, as I mentioned, provide the certificates and keys to your manufacturing partner, and agree a process whereby the manufacturing partner will flash the keys and certificates onto the devices for you. Okay, so that's something that needs to be worked out when you get to manufacturing at scale. To simplify that, we recently announced a new feature for the AWS IoT service for registration on first use, and we refer to this as just-in-time registration of device certificates. There's a blog post available which gives more detail on this that you can see at the bottom right of this slide. And the way this process works is you register your own certificate authority certificate with AWS IoT, and then you use that CA cert to sign your own device certificates. And you obviously get those device certificates onto your devices together with your private keys and public keys. And then when a device attempts to connect with one of these X509 certificates that is not known to AWS IoT but was signed by the CA that is registered with AWS IoT, we auto-register the certificate into a pending activation state. So that happens on first connect to our MQTT or WebSockets endpoint. We put the certificate into pending activation state and it's awaiting activation. At this point, it publishes a message, that's AWS IoT, publishes a message to the MQTT topic that you can see at the top there, $AWS/event/certificate/registered/CA certificate ID. And you can subscribe a rule to that topic, and you can invoke an AWS Lambda function when a message is received on that topic, and you can also see the message format on this slide. That Lambda function can perform a couple of operations for you automatically. It can set the certificate state to active, as you can see there, and it can attach a policy to the device certificate principal, and therefore it can enable the device certificate to access specific MQTT topics and perform other operations via the AWS IoT API. So that is essentially the process that you use for just-in-time registration. There's a full write-up of that process available on that blog post. So if I went through that a little bit quickly, either rewatch the webinar or take a look at the blog post that you can see bottom right, which explains and includes actually the code samples, the policy samples that you need to set all that up. And it also includes the skeleton function that you need for AWS Lambda to do the certificate activation and policy attachment as well. So it's very comprehensively written up in the blog post that you can see there. Now, policy attachment's important. I've mentioned it quite a few times. The policy attachments really are the things that enable your devices to interact with AWS IoT, to connect, to subscribe, to publish, to receive messages, and also to work with the thing Shadow, which we're going to come to in a few minutes. And these are JSON documents. They follow the same conventions as IAM policies. And obviously those actions have unique functions. So for example, the IoT connect action is checked every time a connect request is sent to the broker. The broker does not allow two clients with the same ID to stay connected at the same time. So if a second client connects, the broker will detect this and disconnect one of the clients, and the connect permissions can be used to ensure that only authorized clients can connect using a specific client ID. And you have other functionality on the other policy actions as well. You can find, again, full details on that if you check out the URL that you can see on the bottom right of that slide in the IoT Developer Guide, the section related to authorization. Attaching policies to certificates can be done via the CLI or via the SDKs or via the console. If you want to do that via the CLI, these are the commands that you'll use. AWS IoT create policy, you specify a policy name, and you include a policy document, which is the JSON policy document, referring to those API actions that I showed a second ago. And then the second command, AWS IoT attach principal, linking the policy name for which you've just created the policy for, to the principal, which is the certificate ARN, which is generated when you create your certificate. And that's it really, very simple. And this can allow you to exercise good security practice, a principle of least privilege, when you are establishing device connectivity, only permitting principals to perform operations that are required to support your particular application or use case. So do that, bear that in mind. You should apply a principle of least privilege to AWS IoT applications, just like you should to general application usage in line with security best practices. The AWS IoT Thing Registry. So we've got a fleet of things. How do we identify and manage them? Well, the AWS IoT Registry allows you to establish static attributes associated to things. This can be things like firmware versions, serial numbers, attributes of other types such as voltages and wattages and installation dates and model numbers. So it's a flexible fixed schema that you can use to attach essentially template data to each one of your things, and you can use that for support and maintenance of your fleet. So ways to do that, well, obviously these actions are exposed via CLI, via the SDKs and via the console. Here are the CLI commands. So AWS IoT create thing, specify the name and an attribute payload, which is obviously a piece of JSON that defines attributes associated with that thing. So this would be schemaless, where we have arbitrary metadata that we're attaching to particular things. We can then list them, and you'll see that those attributes will be listed, so they're stored alongside the definitions of the things that we've created. We can also search for things. So AWS IoT list things, attribute name, wattage, attribute value 75. It'll return our JSON structure with all of the things that have the wattage attribute set to 75. So you can use this for filtering and operating on physical devices via the thing registry metadata. You can also define thing types. These allow you to store description and configuration information is common to all things associated with a thing type. So this is schema templating essentially, where you're going to define, for example here, a light bulb thing type. All things associated with the light bulb thing type will share a set of attributes. They'll all share a description, and they'll all have certain searchable attributes set. In this example that you can see here, the wattage and the model would become searchable attributes. For more on the thing registry, visit the URL once again that you can see on the bottom right of this slide. At this stage we've got our prototype devices with our SDK on them, we've got our certificates on them, we've got policies attached to those certs that permit them to communicate with the AWS IoT endpoint. And we have hopefully stored some metadata about those devices in our registry so that we can manage them over time. So now we want to start communicating with things, right? And for this purpose, we have the device gateway. It's a very important part of the AWS IoT service, of course. It allows you to communicate with devices via MQTT and HTTP in a secure and authorized manner. And this is an elastically scalable service, which means AWS provides you with an endpoint. You've seen that endpoint in the demo that I gave of key and certificate creation, where I had the account-specific endpoint embedded within my header file. Hopefully you'll recall that. And you send your messages to that endpoint from your devices, and AWS takes care of making sure there's sufficient capacity in the endpoint for whatever volume of messages you happen to be publishing. Also, we take care of scaling, failure condition management and maintenance, so it's a managed service, and that endpoint supports the MQTT protocol. Obviously it also supports WebSockets, and WebSockets is more commonly used for components of IoT applications that might run in browsers, for example, where you want to have browser-based control for your IoT fleet. You could send messages to your MQTT topics over WebSockets to enable that. So we're protocol agnostic really, MQTT or WebSockets, but they have fit specific use cases. MQTT particularly is excellent for power and CPU constrained environment where resources in constraint, and you want to make very efficient use of client resources, particularly from a power efficiency perspective. So you can see there 170.9 times less battery to receive data to MQTT. This is really by virtue of the lightweight nature of the protocol combined with the mutual certificate-based TLS authentication that takes place. So there's no need for session key generation, which is a very computationally intensive part of the process here. And as I said, our gateway is a managed service. You can send as many messages as you want through the gateway. It's highly scalable, and AWS will make sure there's sufficient capacity there. Once you've got your messages flowing through the gateway, you can operate on them using the AWS IoT Rules Engine. This allows you to transform and route messages based on rules. And it's a very powerful component of the AWS IoT service, actually. So the rules engine will inspect attributes within the messages that are flowing through the gateway, looking at MQTT topics that have messages published to them, and it can extract messages from those topics and it can evaluate them, and by evaluating it can route messages to different destinations. Here you can see an example, simplistic example of message republishing and also of messages being archived inside Amazon S3. That's a simple storage service for long-term usage and also for real-time analytics. So it's a very simple example of how you might put the rules engine to work for a specific application. Now, how does it work? Well, use a SQL style syntax here. So for example, select star from thing/thing2/color, where color equals red, would result in all messages on that specific topic that had an attribute called color, which was set to value red, being forwarded to a particular action or to a particular destination. And there are built-in functions here for things like string manipulation, mathematical operations, context-based helper functions, cryptographic support, and also specific attributes that can be embedded in your messages by the gateway. So for things like timestamp, UUID, random numbers, etc., they can also be generated by the rules engine, inserted into messages if you need that. So you can perform things like switching state. Here you would receive a message with a particular attribute, color value red. You'd receive that. There'd be a rule in the rules engine, and that could republish on the other topic to change the state of another device on the basis of a received message. So that's a very simple example of logic-based control implemented within AWS IoT without any server infrastructure. So the rules engine does everything for you that's required for that particular use case. You have nothing to deploy, scale, or operate or manage failure conditions on. Really very, very, very simple. So simplicity is one side of the coin here. The other side of the coin is flexibility and power. So here you can see a more complex statement within the rules engine. And what we're doing here, first line, select star client ID as MQTT client ID. This is an embedded function within the rules engine. So we're going to extract the client ID that is emitting or has published the message that we've received here. And we're going to embed that within the message that we forward from this rule as an attribute called MQTT client ID. So that's a built-in function that we're making use of there. Then we're reading from a specific topic, which is one/rule, and we have a where statement here, which starts with topic 2. So the second part of the topic starts with the characters IME33, and there's some other attributes that we're reading. The state attribute or the hydro temp attribute, and obviously we've got some logical operations there. We're looking for state equals in it, or the hydro temp exceeds the surface temp attribute. And then the actions, well, we're going to republish this message back on a topic called, and the topic name's constructed dynamically here, controllers $substring. It's another built-in function, and we're going to extract the third to the fifth characters of the third part of the topic name that we originally received. So we can perform powerful logic-based assessment and also transformation of messages that flow through the rules engine using these built-in functions. And there's full documentation, of course, on those built-in functions in the URL that you can see on the bottom right of this particular slide. So just wrapping up on native rules engine actions. This allows you to perform complex evaluations responding to a fleet of things rather than just single units. And those built-in functions, of which there are dozens available, make that a whole lot easier to do without having to run significant back-end infrastructure in your own right. You can also perform multiple or simultaneous actions by routing messages to multiple service endpoints. And it's probably worthwhile moving on now and talking a little bit more about service endpoints. And this is something that we talked about briefly at the beginning of this session, the fact that there are a lot of uses and use cases for AWS in the context of connected device or IoT applications that predated the existence of the AWS IoT service. So customers wanted to use AWS to build these kind of applications because of other AWS services that already existed. and obviously integration between the AWS IoT service and pre-existing and new AWS services is an important aspect of delivering value to customers here. So how does that work? Well, the AWS IoT Rules Engine connects AWS IoT to external endpoints and to AWS services. So when setting up new rules within the AWS IoT Rules Engine, the actions for those rules can result in forwarding your AWS IoT messages directly to other AWS services through a direct integration capability. At the moment, this includes AWS services such as Amazon S3, DynamoDB, Amazon Kinesis, the Simple Notification Service SNS, AWS Lambda, Amazon SQS, and others as well actually that have been added since launch. So those are powerful direct integrations that you can use to build high value functionality directly within AWS IoT based applications. You can also integrate to external endpoints via SNS or via AWS Lambda. So this allows you to take your AWS IoT messages and republish them to other web services endpoints via SNS, or to use them in the payload for requests made to other external endpoints. This is pretty powerful with AWS Lambda actually, because obviously you can embed API credentials for other services in your AWS Lambda code, and you can use that to call out from AWS to other services. There are also services elsewhere within AWS that can be reached via intermediary services such as Amazon Kinesis, Amazon Kinesis Firehose, Amazon Kinesis Analytics, AWS Lambda, Amazon S3 and others, and this can allow you to get your AWS IoT data into services such as the Relational Database Service, Amazon Glacier, Amazon Elastic MapReduce, Amazon Redshift, Amazon Elasticache, EC2, and a variety of other services as well. And customers essentially compose applications by using these services in combination. So as I mentioned, this works by evaluating inbound messages published into AWS IoT, performing transformations, which you'll define in rules, and then delivering those messages to the appropriate endpoint based on business rules that you might specify. As I said, external endpoints can be reached via AWS Lambda and via SNS Simple Notification Service. There's a wide variety of different actions available to you. For example, you can invoke Lambda functions, you can put objects into S3 buckets, you can insert, update and read from DynamoDB tables, you can publish to SNS topics or endpoints, you can publish to Kinesis streams, you can publish to Amazon Kinesis Firehose and have that stream data persisted. You can also operate on those streams with Kinesis Analytics, and you can also republish messages to specific AWS IoT topics. So it's a very powerful collection of services that you can use to build connected device applications, IoT applications, with the minimum amount of infrastructure operations. When we are talking about the rules engine, we're talking there about messages that are sent from devices to MQTT topics, which the rules engine is effectively subscribed to. Now there is another alternative mechanism for communicating with devices which is asynchronous in nature, and this is the device shadow. You might recall from the beginning of the session we discussed this briefly. This is a persistent representation of device state which is stored in a virtual representation in the AWS Cloud. And this allows you to read and write device state when devices are not connected. So devices will connect and synchronize with the device state intermittently, or may connect and synchronize with the device state intermittently, the state stored in the shadow. And this can provide as you can appreciate, a useful platform for any type of connected device application which has to deal with intermittent connectivity or intermittent power. Here's an example with a spectrometer where the spectrometer runs intermittently, goes offline when it's completed, but it stores its last reported state in the AWS IoT device shadow. And that allows technicians to communicate with the spectrometers asynchronously from within mobile apps. So what we're doing here really is storing a representation of the device in a document database and making that available via a web services API, which is async, so you can communicate with that. reading a representation of the device as we've specified, even when the device is not actually online. So how does it work? Well, the device SDK has within it, these are the AWS IoT device SDKs, have within them shadow functionality, so synchronized shadow methods essentially that can be called through the different programming and language models that are used. They can be called, and if you do that, you will publish the current state to the AWS IoT shadow. You can then, from your application, that state is then persisted in that JSON data store that I talked about, and your applications can request that device state. When they request it, they receive it back from the JSON data store, not from the device directly. They can also request state changes. Those in turn are stored in that JSON device store. And the next time the device SDK calls the sync shadow method, they'll receive the updated shadow state. They'll then publish back their current state. That'll then go back into that JSON store, and that will go out to confirm the state change. So you have this asynchronous model for communicating with devices that may or may not be online, useful in intermittent connectivity scenarios, and also in situations where power is intermittent. So low-powered devices, for example, that might go to sleep for an extended period of time, then periodically wait and publish data, so they're not transmitting all the time. So it's a very powerful feature. The things can report their state to one or to multiple shadows, and they can retrieve their desired state from the shadow. The shadow itself reports delta, desired and reported states, along with a version and metadata. And then apps, either mobile or web apps that you might write, can set the desired state of devices, can get the last reported state, and can actually delete down and clear the shadow as well if they're authorized to do so. And the state is stored in said document-orientated database, so in JSON structures, which look a little bit like this. So desired, reported, and delta. You'll see that our desired state, we want our lights color attribute to be set to red and our engine on. The reported state, the lights are green and the engine on, so the delta is calculated. And it's that delta which is sent to the device on the synchronization operation to minimize the amount of data that needs to be transmitted across those MQTT topics. Now, our SDK means that you can build shadow functionality into your devices very simply. We support the shadow in all of the different SDKs that we provide. Under the hood, there are actually 4 MQTT topics that are in play here. And it is MQTT that is used to publish the shadow state, but the device SDK abstracts that away, so you don't have to deal with these topics. You're dealing, as I said before, with calling appropriate methods in the SDK, and when you call those methods, the topics are abstracted. Underneath the covers, the topics are used, but you are dealing with shadow, not with the topics. So it really simplifies the process of building applications that need this asynchronous connectivity, and where you might want a virtual representation of your device to be persisted in the cloud. One of the situations where this is used, or can be used, we recommend that it's used, is in updating device firmware, where the device firmware can be stored in S3, so placing your version firmware distributions in S3, using either topic patterns or shadow updates to publish firmware updates to a fleet of devices, sending a URL to the S3 download, and then the devices themselves fetching their firmware updates directly from S3. So this avoids having to publish very large messages over MQTT topics, makes the system more distributed, and you can also use the rules engine together with DynamoDB to keep a state track of update progress as well. So this can make it easier to manage firmware updates. The last topic I want to talk about is retiring or replacing devices. It's a very short topic because it's very simple to do this. So simply to revoke connectivity from a device to AWS IoT, you're dealing with the certificates that are associated with the device principals that you've created, and to revoke connectivity from a specific device is as simple as just updating the certificate associated with that device and putting the status of that certificate into the revoke status, at which point the certificate will no longer be accepted by the gateway and there'll no longer be access to any topics associated with that particular certificate. Once you've done that, it's then just a matter of creating and deploying a new device with new certificate and new keys on it, and then you attach the same policy to the new device's certificate, and that new device will then be furnished with the same access permissions as the device that you've retired, and it will have exactly the same facilities and capabilities to make use of the AWS IoT service. Okay, so that concludes our trip through the life cycle of a thing using the AWS IoT service. I'd encourage you to download the slides that will be made available after this session on the AWS SlideShare. There were quite a few links, as you'll recall, at the bottom of some of those slides which contain references to further documentation about a lot of the topics that we've discussed here. There's a lot more depth in the documentation, obviously, than we have time to go into in a 1 hour long webinar. I also mentioned at the top of the session some guidance about getting started with AWS IoT, including access to our SDKs. And if you go to awsamazon.com/IoT, that's the IoT product page on the AWS website, you'll find a great collection of resources there that can help you learn more about this service, use cases, technical documentation, developer guides, all kinds of resources that will help you in building connected device applications. You can also, of course, reach out to us via your account teams, via the Contact Us capability on the AWS website if you've got questions or you need help from our solutions architecture or account management teams. And we do have AWS IoT specialist solutions architects available as well that can help customers that are trying to build connected device applications using the AWS IoT service and the platform that represents. Last thing for me to do is just to thank you for joining today's session. Do find me on Twitter if you're interested in keeping up with what I'm up to. And I'm going to turn the session over now to our Q&A team, who are going to answer some of the questions that have been submitted in the course of today's session. If you do have further questions, please do submit those using the Q&A interface in the webinar interface. We'll keep the Q&A open while we answer a few of your questions. I want to thank you for joining me for today's session. Goodbye.
So this time I'd like to extend a special thank you to our presenter Ian today for the great presentation, and Ryan for answering all the audience's questions through our Q&A panel. If you have any comments on our previous or upcoming webinars or suggestions on the topics that you wish AWS to cover in future webinars, please feel free to email us at aws-webcasts@amazon.com. Your feedback will help us improve our webinar programming. I'd like to thank our audience today for coming in and giving us all the great questions today. At this time, you can disconnect. Enjoy the rest of your day, and thank you.